Let's have a look at microcontrollers. So the Arduino board has, at least Arduino Uno, has got the Atmel Atmega 328B chipset on it. And so we're just going to be looking at a few of the features of these specific microcontrollers. And then we will, after we've looked at that, we'll be able to have a better understanding when we get into the programming side of things. Alright, so this is a 8-bit microcontroller. It's some of the things are being features are being explained over here, and so I'll just be highlighting a few that might be might be important and might be worthwhile just mentioning. So these features came from the datasheet specifically of this Atmega 328B microcontroller. And it's got a lot of information in it in terms of, it's got an EEPROM in it, it's got a flash program memory in it, in terms of the sizes that it's got available, how many flash cycles and EEPROM cycles you can have. So you can write to this Arduino board about 10,000 times. Data retention period, you're looking at the independent lock bits in the boot code section. It's optional, and it's got all the details over there. What is probably of more which will be more important for you to look at is how many timers and counters it's got. Well, it's got two 8-bit timers and counters. It's got one 16-bit timer or counter. These 16-bit timers can be split up into two 8-bit timers if need be. You've got real-time counters for separate oscillators. So in other words, these can run in the background. We do not need to continuously activate them and change them and have our code stopped while it's running in the background. So it is able to run in the background over here. It's got 6 pulse width modulation channels, which can be useful. These 6 pulse width modulation channels are based on these timers, so one needs to keep that in mind. It's got 8 10-bit A to D converter pins on it. It's got a programmable serial USART or the UART that you can do. So that's important if you want to communicate with it. Like I explained, you do get your SPI, you get your 2-wire serial interface, you get the I2C compatibility, and those things should you want to use it. If we keep on going down over here, you get different sleep modes, if you should want to use those type of features. You've got operating temperatures, which is important. You don't want to sort of go and blow this thing up because it was maybe in too high temperatures or too low temperatures and not understanding why things aren't working. You've got operating voltages. So the minimum voltage is 1.8 volt to 5.5 volts. Obviously, these voltages need to be taken into account with these chips. So our Arduino board has got a set regulator onto it, which will allow you to operate on 5 volts. But the chip itself has got a feature that can operate on lower voltages. Yet if you take into account that you've got 1.8 volt as your maximum voltage, at least what you're connecting to that, if there's any fluctuation in the volt, maybe with a slight volt drop, it could cause your microcontroller to reset. So you don't want to go too low over there necessarily. We've got 23 input-output lines as well. This is a 28 PDIP type of chip. There are also surface mount ones available. You got a speed that you can operate between 0 and 4 megahertz or up to 20 megahertz or so, depending on the voltages that are applied to it. So that's also important just to keep in mind. In terms of low voltages, will have a restriction in terms of what frequencies you can operate on that and also the speed of this microcontroller. On power saver mode, you're using about 0.8 microamps. If we go to the top over here, I just want to see if there's anything in terms of current over there. Nothing that I can see over there offhand. Okay, so that's sort of the features of it and what this specific microcontroller is able to do. This is a layout of it for the DIP package. And we have had a look at this already in terms of what all the input and output pins are. So those are just again to be available. And what I'm doing, all these things that I'm mentioning, this document, I'm going to make available online as well. I will place a link down at the bottom of the video so that you can also scroll through this and use this as a reference later on. Okay, this is the block diagram of it. Something I wouldn't expect anybody to know off by heart or so, but it's just to give you a breakdown of, you do have a port C, a port B, and a port D. You've got your different communication protocols over there, like the two-wire interface, the SPI, and the UART. It's showing you that you've got obviously your voltages over there. You've got your analog to digital conversion. You've got all these different features that are taken into account. So this is essentially what it's able to offer you. Again, they're just more for in terms of a reference, should this be something that you would want to look at. Okay, so the next thing we're going to be looking at is the interrupt. And so for this Atmega 328P microcontroller, it's got the following interrupts, and this specific table is quite important. It's not important in terms of which vector number correlates with which interrupt or so. It's more important in terms of which order these interrupts are. So, for example, you've got the external interrupt that is a specific pin on a microcontroller. You've got external interrupt 1 and external interrupt 0. You've got your timer interrupts over here, which you might use. You've got your UART interrupts in terms of receiving data. You've got your interrupts for analog to digital conversion, should you be using that. The problem comes in, and it's been an issue often experienced with projects, is that, for example, you've got, let's say you're busy monitoring a motor speed. And so you are busy coming and using your external interrupt 0 to, every time that the encoder gives you a pulse, you're going to be checking it, and you're going to use it to check if channel B is a 1 or a 0, and then you're going to keep count of how many pulses have happened, and therefore how many revolutions and the speed of the motor. The thing is, though, in these interrupts, which is essentially procedures in your code, you want to minimize that code as much as possible. And the reason being is that if you look over here, your UART RX interrupt is lower down in the stable. Okay, so should this external interrupt be operating and checking for pulses and stuff, if during that time you should be receiving any data on your serial input, this data will go lost because this external interrupt's got a higher priority. So if you go and you start busy receiving data on your UART, and you're busy getting this information from this computer, and in between that your external interrupt gets activated because of a pulse has been received, this code over here will stop. and this external interrupt code will be then initiated and first executed, and then it will come back and continue to read the data. If your procedures are too large in these external interrupt requests, you do have a chance that when data is received on a UART, you're not going to be able to, the microcontroller is not going to recognize and store it. So these interrupts have got a different priority, going from the top with higher priority coming down to the bottom. And so you need to just keep in mind that the high priority interrupts do have priority in terms of they will be activated if any of the other interrupts below it should be already running. And due to that reason, you want to basically use your procedures for your interrupts just to set flags, maybe just to keep record of maybe some number, and then in your main code you would then go and use that to do some analysis. So we'll have a look at it, but you need to keep in mind that these interrupts have got some procedure in terms of a higher value than others. Okay, let's have a look at registers. So registers are these variables that's on a microcontroller, and these are essentially your settings for the microcontroller. Okay, so let's say we had to look at port A. Okay, I know that for this specific microcontroller we do not have a port A, but it might be a port B data register that we're looking. This data port A data register, you've got to indicate in terms of where the pins are, input pins or output pins, and that's offset over here. So essentially what you would do is you would say, well, if for this data register or data direction register over here, if any of these pins should be need to be set to 1, it will correlate into an output or to an input. So if you look at the data sheet over here, or the information is supplied over here, if bits 4 to 7 would have to be set to logic 1, and that would correspond as output. Okay, so if any of these bits over here are 1s, it will indicate that those are output pins. Okay, so then what we would have to do is we would have to convert that and say, well, that's a 1, that's a 1, that's a 1, that's a 1, because we want bits 4 to 7 or pins 4 to 7 for this specific port to be output, while the others would be considered as input. And then we've got to go and set this register DDRA to be 0B. 0B refers to it being a binary number, and in a binary code we would have to place behind it, so that would be 1111 to indicate that those first 4 bits over there are output, and then 0000 to indicate that the next 4 bits are input. Or you would have to use hex, 0x, which will refer to hexadecimals. Or you could use a normal decimal number. That would mean you'd need to convert this binary number to a decimal number and then assign it that specific value. Okay, so often we do change pins to be inputs and outputs for special occasions during your code, but generally you would set this initially in the beginning. Okay, if you're looking at your general interrupt control register, so if we want to use, again, this specific microcontroller used in this example, it's got an external interrupt 2 as well, not only just 0 and 1, but it should give you an idea of where we're going with this. So if we want to activate interrupt 0 or interrupt 1, we need to set those bits respectively to be a 1, and then assign that specific register. You would see that the details are indicated over here below in terms of interrupt 0, interrupt 2. You know, if set to 1, then that means that that interrupt is set. So if you have a look at the data sheet, that's going to mean that you need to look at each individual bit for about 50 registers as a minimum to be able to see which ones you're going to need to be activated and stuff. Then you need to go and convert those bits that would be consisting of 8 bits into a number and assign it to that specific register value. And so, just as we did over here with the DDRA, we indicated which were output pins, we indicated what were input pins, and we then assigned that value to that specific register. And you could be doing this, and to be honest, it will take you, if you know what you're doing and you're familiar with what all these register values need to be and stuff, and you've got the datasheet for you, and you can probably read through it and go through in the different sections in the datasheet. The datasheets can easily be around about 200 pages in length. It'll probably take you about a good day or two to be able to generate all the register values that you need for a specific application. And therefore you would already have your electronic circuitry completed. You know what's going to be inputs and outputs so that you can correlate to them in your programming code. And so it can be quite a time-consuming process. Yet that's what makes this codevision AVR or CVAVR very useful. Okay, so with codevision AVR or CVAVR, we've got this wizard, the code wizard AVR, that you can run. And the different versions have got different sort of layouts of these wizards. Over the years they have changed a bit, but essentially you're able to indicate what chipset you're using over there. You're able to indicate which clock speed you're going to be operating on in terms of what is the speed of the crystal that you're using. And you're able to do a whole bunch of different settings on it, which we will look at in the next session of the video as well, or one of the following videos at least. But this gives you or allows you to do these settings, and in the code wizard AVR goes and generates all this code for you. And we will have a look at this when we do this, the programming part of things. So it will generate the code that will be for the values that's assigned to registers, depending on what settings you give it over here in terms of your configuration and what's going to be inputs and outputs, and whether you're going to be using an ADC or not, or whether you're going to be using a UART or not. And then it will generate that code, and then you can just focus on using the code and programming code that will be for checking inputs and checking outputs and alternating different pins and different configurations. Okay, so the evaluation version or the non-commercial version of CVAVR can be found from hpinfotech.ro/CVAVR-download.html. So the different versions are also available there that you can download, and it's really easy to install. So when you install it, you do not need to install Atmel Studio or AVR Studio. First, sometimes some people might say, oh, you need to do it. I've given it a try without installing it, and it works. A bunch of windows will be popping up asking to install different things. Just saying yes, click next, install the different things. It will even install the drivers that will be required for the USB to allow you to communicate with the Arduino board. So that's also one of the options, and Windows will pop up and allow you to program. Okay, now that we've looked at this, just before we continue with looking at the programming things, which we'll look in the following video, you need to be aware of this diagram. Again, something that I found from this specific link. Like I indicated, it's not useful. It's got other useful information about the Arduino software as well, which is not really useful for codevision AVR or CVAVR. But what is useful is a pin layout. And like we've seen before in one of the previous videos, it gives us a good correlation in terms of how different pins on our Arduino board correlates with the different pins and ports that we've been looking at on a microcontroller, and therefore we're going to be using this information to program specific pins and give them certain outputs and look at what inputs they are. Okay, so this gives you a quick overview of how the microcontroller operates, some internal information about the microcontroller. Again, a lot of this might sound a little bit confusing to you at the moment, just because once we start looking at the programming side of things, it will start becoming more familiar. But things like the internal interrupts and stuff, now you can sort of see how the hardware code relates to the external circuitry. So that's why it's important to make sure your external circuitry is in place before you even start looking at programming, so that you know which pins you're going to be operating and working with. And so we'll be looking next at the different, or how we'll go about programming this. Before we even do that, we're going to be just looking at the overview of what programming techniques and features you can do by using the C language.